Hello everyone. Good morning. Yesterday we saw, today we are seeing. Hope everybody is doing good, right? So I hope I. Good morning. Good morning. So we have how many? We have 12. Fine. I think we have enough people. I think we can start right away. Right. Okay. Let me share my screen. Okay. So hope you remember what we saw last class, right? Maybe we'll have a very quick recap of whatever it is. Right. So we saw the formula for radius, that is 0.059 by 2, and this has to be changed, right? This has to be changed to nanometers, right? I told you that. Okay, then velocity is this 2.18 divided to the power 6 z by n, and then energy of the nth orbit, which is minus k z squared by n squared. I told you k will depend on what kind of unit you want it to be, right? So it is 13.6 in terms of electron volts, or it will be 2.18 in 10 to the power minus 18 in terms of joules. That will be the K value, right? Okay. Now, we went on to see what is the transition energy, right? Transition energy is basically when electron shifts from one orbit to another orbit. Obviously, energy will be released or energy will be accepted or absorbed, depending on whether it's going from lower orbit to higher orbit. Lower to higher orbit, energy will be absorbed. Higher orbit to lower orbit, energy will be released, right? So then we went on to see that the transition energy formula is delta E is equal to final energy minus initial energy, wherever the electron going to finally and where it was initially. And with that, I think we got a formula. Where is it? I think it will be there at the last. Right? 1 second. Where is the formula? 1 by n1 squared minus, yeah, exactly. This one. Right? So this is equal to EF minus EI, which is KZ squared minus 1 by NI squared minus 1 by NF squared. NI is the why, like it should be basically NF minus NI, but I have a negative sign if you remember in your what is that K, I mean energy equation. That's why it's changing like this. Okay, so it is KZ squared into 1 by NI squared into 1 by NF squared. Okay, NI is the initial orbit, NF is the final orbit. Okay, then we went on to see what is the ionization energy. What is the modern definition? Modern definition is electron coming out from the valence shell. But here in case of Bohr's, we said that it is the energy required to take the electron from first orbit to the infinite orbit. Okay, first orbit to the infinite orbit. Okay, now that if you substitute, you will be getting IE is equal to K into Z squared. Very simple formula, because Ni will be 1 constant, because from first orbit to the infinite orbit, so it will go 1 by infinity will become 0. So all you have is nothing but KZ squared, right? And very importantly, I told you that this Bohr's atomic theory will work only for single electron species, right? It will work for He plus, it will work for Li2 plus, it will work for H alone. But if at all you have helium or lithium, no, it will not work, right? So that I said for first ionization of helium will not be, I'll not be able to do this. I'll be able to do it for second ionization enthalpy of helium, because this only He plus contains 1 electron. He will contain 2 electrons, right? Same goes with lithium also. Lithium I'll be able to find only the third ionization energy, because after Li plus is formed, then only, I mean, yeah, after Li plus is formed, only then it has just 2 electrons, 1 electron. Sorry, after it forms Li2 plus, then only it has 1 electron. So I'll be able to find the third ionization energy, right? Okay, so these are all the formulas we listed out, right? Rn, Vn, energy, transition energy, ionization energy, and then we did a couple of problems also. Okay, right? That's what we did. Anything else? Yeah, and this is very important. We got this Planck's equation, right? This is what is Planck's equation. E is equal to h nu. And I told you what exactly is this frequency. Frequency is nothing but number of cycles per second. Say this is 1 cycle. I will tell if I can use some other color, right? This is 1 cycle. This is the second cycle, right? Like that, in 1 second, how many cycles you undergo? That is what is my frequency. Okay, and there is one more term regarding your waves, that is my wavelength, right? Wavelength is nothing but, okay, first before that we have to understand what is this crust and what is this trough. Any wave will have a maximum value and a minimum value, right? The maximum value is what is called as crest, and the minimum value is what is called as trough, right? So wavelength, if I say lambda, lambda is nothing but the distance between two consecutive crests or distance between two consecutive troughs. That is what is called as wavelength. Okay, and there is a connection between your frequency and lambda, that is wavelength. Frequency mu is equal to c by lambda. Okay, now if I know this, and I know what basically c is nothing but the speed of light, 300 to the power minus 300 to the power 8 meter per second. Now with this equation, that is E is equal to h nu, in place of mu I put c by lambda, then you will be getting this equation as E is equal to hc by lambda, right? Okay, fine. Then we can connect this with the delta E. Delta E I know is basically kz squared into 1 by ni squared into 1 by nf squared. Now this E is also energy. That will be equal to hc by lambda, right? So h is a constant, c is a constant, k is a constant, right? So if you just bring 1 by lambda alone, you keep it this side, 1 by lambda, hc you bring this side, k by hc will become a new constant called as Rydberg's constant, right? Rydberg's constant value is this much, 1.097 into 10 to the power 7 per meter. Right, and this 1 by lambda is again a new value. 1 by lambda is what is called as wave number, and is denoted by the letter mu bar. Okay, so we can write 1 by lambda is equal to this, or we can write mu bar is equal to this, rh into z squared into 1 by ni squared into 1 by nf squared. Okay, so this is where we stopped last class, right? So we'll continue for today. Let me make a new page. So today is 25. Okay, before that, you are 11th, 25, 0, 7. Right, cool. So fine. Now today, or maybe we'll do some couple of problems. Okay, before that, right? There is this thing called as, okay, I'll use this one little. Right. So there is this thing called as emission spectrum of hydrogen, right? Very important, right? Emission spectrum of hydrogen. Okay, so from the name itself, you understand we are going to talk about emission spectrum, right? We know spectrum. Spectrum is basically quantity, right? The line spectrum or continuous spectrum. Basically, we'll be getting only line spectrum. We know that, right? If you have any kind of thing, according to Planck's thing, we'll be getting only line spectrum. Okay, so when I say emission spectrum, basically energy is getting released. Right. So for energy getting released, obviously you have to understand that the electron has to come from higher orbit to the lower orbit. Correct? Right? For the emission to happen, right? For if at all emission of energy has to come out. For that to happen, the electron has to shift from a higher orbit to a lower orbit. Correct? Right? So I have basically we're talking about the energy values for emission spectrum of hydrogen specifically. If electron comes from a higher orbit to lower orbit, what kind of energies will be liberated? That's what we're trying to see. Okay, so for me to calculate the energy, it is going to be the same transition energy only, right? Delta E, or we can even write 1 by lambda, whatever it is. Delta E or 1 by lambda is equal to RH Z squared. Now, in this case, people, look at this. The formula will be little different. Why? Because actually I have to, fine, I'll write to this thing. Say, look at this. When I normally write, it is RHZ squared into 1 by Ni squared into 1 by Nf squared. We write it like this. Now, this is both for emission as well as for absorption. Is it not? Right? When electron goes from higher orbit to lower orbit or from lower orbit to higher orbit, this equation holds good, and except that the the energy value will be positive or negative depending on whether it's going to be absorption or emission. Okay, now since here we are talking only about emission, right? The equation will little change. There is not much changes. It is very simple. It is 1 by N1 squared divided by 1 by N2 squared. Now this N1 is the lower orbit, and this N2 is the higher orbit. Very, very simple. Now here it was different, right? Here it was initial and final orbit, depending on where the electron goes from. But here it is defined that it is going to come from a higher orbit to a lower orbit for sure, because we're talking about emission spectrum, right? So this N1 is the lower orbit, N2 is the higher orbit. Very, very simple. Do not get confused between these two. These two are very, very similar equations. If I write Ni and Nf, it is both absorption and emission, right? But if I write N1, which is a lower orbit, N2, which is the higher orbit, right? That is only for emission spectrum.
Sir?
Yeah.
So then what about the energy when absorbed by the electron when it's moving from first orbit to second orbit?
Yeah, that for that cases we'll be using this equation. Whenever absorption is happening, I'll be using this first equation. Okay. Yeah.
So then that will also be.
That would also be
same as this formula, no sir? N1 square minus N2 square.
Correct, correct. This exactly this particular thing is derived from this only, but this is done only for emission. That's it. There are reasons to this. Why? Because different scientists worked on different parts of the spectrum, right? Say, like, if I can just move on, we'll understand why am I talking like this. There is this guy. The first guy was the first scientist called as Lyman. Okay. Now for Lyman, what he did is this N1 and N2 are going to be only different, right? All the other things are constant, right? RH is constant, Z is constant, right? Obviously for the element it is constant, right? So this N1, depending on the N1 and N2, different values of lambda, different values of energy I'll be getting. Correct, right? So this Lyman guy worked on the case where I had N1 is equal to 1 and N2 can be anything. N2 can be 2, 3, 4, 5, 6, so on and so forth, right? So Lyman worked like this. Say this is the N is equal to 1, the first orbit, second orbit, third orbit, fourth orbit, fifth orbit. So wherever the electron is, say the electron is here or the electron is here, it has to come to the first orbit. And obviously if it comes, energy will be released and that energy can be calculated with this. Okay, do not confuse between these and do these. I would say if you're getting confused, forget about it. These two are similar only, right? But I would say you don't have to, one second, you don't have to remember this equation, but at least remembering this equation is very important, because questions will come from this only. Yes, ask your question. Yes, what is it?
Energy becomes same, right?
Your voice is breaking, Kanna. What is it?
So then the absorption energy and the emission energy when electron is going from first shell to second shell and when it's coming from second to first shell will be same, right?
Absolutely, it is going to be same. Absolutely, why not?
Sir, but then yesterday you told that it wouldn't be same.
Oh, why? See, if it is first to second and second to first, there will not be any difference. But say when the electron is in, say when the electron goes from first to third orbit, okay, and okay, this is there, electron is in the third orbit now. Now when the electron comes back, it is not necessary that electron will directly shift to the first orbit only. It might shift to the second orbit, then it can come to the first orbit, or it can directly go to the first orbit. So obviously the energy absorbed and energy released will be different, because if at all it comes directly from third to first orbit, obviously energy will be same. But if it takes some other path, say it goes to second orbit and from second orbit goes to first orbit, definitely the energy absorbed and energy released will be different. Hope you're getting the point.
Okay, sir. Yes, sir. Understood.
Right? Okay, fine. So all you have to understand is this formula now. 1 by lambda is equal to r h z squared into 1 by n1 squared minus 1 by n2 squared. N1 is the lower orbit, n2 is the higher orbit. Okay, right. Now going to Lyman series, it's called Lyman series, right? So what I'm trying to say is that he made sure that the N1, that is where the electron is coming to, the final place is the first orbit. And it can come from any other higher orbit. Say this is the first orbit, right? This is the first orbit, n is equal to 1. Electron can come from directly to here, or it can come from here, it can come from here, it can come from here. It can start from anywhere, but it has to end with n is equal to 1, the first orbit. Okay, so for Lyman series, it's very simple. 1 by lambda is equal to RH z squared into 1 by 1 squared minus 1 by n2 squared. N1 is equal to 1, N2 is anything other than 1, starting with 2. It can be anything. Okay, right. Now, what he understood is that he was able to get like obviously all these energy will be released, right? For all these energy will be released. Okay, so he found that the energy spectrum is coming under UV spectrum, UV light, like the energy which is released is in the form of UV radiations. That's what he understood. Okay, so for Lyman series, two things you have to understand. Where it ends with first orbit. It starts with any other orbit higher than the first orbit. Okay, and second thing what you have to understand is that the energy radiation which is coming out is in the form of UV radiations. Very, very simple. Okay, so like this, I can actually tell you what are all the things. I have Lyman, Balmer, Paschen, Brackett, and Fund. Right? These are different scientists. Okay, who worked on different N1 values. Okay, for now, just now we saw for Lyman N1 is equal to 1, N2 can be starting with 2, 3, 4, so on and so forth. For Balmer, N1 is equal to 2. It is constant. This is constant values. For Lyman, it is N1 is fixed. For Balmer, N1 is fixed as 2. And N2 can again start with 3. Right? Anything higher than 3, not 1 again. So 3, 4, 5, so on and so forth. And what you have to understand is this was UV radiation. Right? Now this was visible. That is normal light, the red color light, green color light, all these things, visible light. Okay, for Paschen, N1 was 3 and N2 starts with 4, 5, 6, 7, so on and so forth. And here you get IR, infrared radiation. Okay, you get infrared radiation. Okay, next for Brackett, N1 is equal to 4, N2 starts with 5, 6, 7, so on and so forth. Here also it is IR. And for Fund, N1 is 5, N2 starts with 6, 7, 8, 9, so on and so forth. Here also it is IR. Okay, so these things has to be there in your fingertips, right? Lyman, you should know the order also. Lyman, Balmer, Paschen, Brackett, Fund, right? Starting with N1 is equal to 1, 2, 3, 4, 5. N2 will be the next starting value, right? And you have to know what part of spectrum the energy is released. In case of Lyman, it is UV. In case of Balmer, it is visible spectrum. And in case of Paschen, it is IR. All the other three are IR, infrared radiations. Okay, right? Very, very simple. Very, very simple. The N1 value is fixed. If at all a particular series is asked to you, N2 is what will be changing. Okay, right? Fine. And the question will be asked like this. The question can like how the questions will be asked is like one question can be like this. For largest lambda, right? For largest lambda in Lyman series, right? For largest lambda in Lyman series, what should be the N2 value? Something like that can be asked, or it can be like, what is the smallest value, right? For the smallest value of lambda in Lyman series, what should be the N2 value? Something like the questions will be asked. Okay, right? Fine. Now understand that for maximum lambda, for lambda max, for the maximum value of lambda in any series, okay, for maximum value of lambda in any series, N2 should be, see, please understand, when I have lambda maximum, look at this equation, E is equal to HC by lambda, right? So if lambda is higher, energy is lesser. Okay, so if I have maximum value of lambda, I am basically going to have minimum value of energy, right? As E minimum. Okay, for E minimum or lambda maximum, N2 is nothing but N1 plus 1, right? For example, this question, I asked you, what should be for me to get the largest lambda value, what should be the N2 value in Lyman series? The answer is, I know for Lyman series, N1 is 1, right? N1 is 1. And I know, so obviously, for the largest lambda value, N2 should be 2. Very simple, N1 plus 1. Right? Same way I can ask you for a Balmer series. Balmer series N1 is 1. So for maximum lambda value, the N2 should be 3. Okay? Same way for
Sir, why should N2 be N1 plus?
okay, that's a good question. Right, look at this. Say we talk about Lyman series. Okay, say now this is n is equal to 1. This is 2, this is 3, this is 4, this is 5. Okay, now say answer this question. Say electron comes from 5th orbit to the 1st orbit, and say electron comes from 2nd orbit to the 1st orbit. Now say this is some E 5 to 1, this is E 2 to 1, this energy, right? Now tell me which energy will be greater. This will be greater, this will be greater. 5 to 1 or 2 to 1? Think about it and tell me. When electron shifts from 5th orbit to the 1st orbit, comparing that energy with the transition of electron from 2nd orbit to 1st orbit, which will be higher, 5 to 1 or 2 to 1?
5 to 1, sir.
Absolutely, no doubt, right? Obviously, electron is coming from 5th orbit to 1st orbit. There is a lot of amount of energy released. So no doubt that the 5 to 1 will have larger energy. Okay, say if I compare it from 6 to 1, 7 to 1, 8 to 1, the energy keeps on increasing. So where do I have minimum energy for a Lyman series? It is obviously the transition from 2 to 1. Say 3 to 1 will have higher energy, 4 to 1 will have still more higher energy. So what I understand is that for Lyman series, E, that is the transition from 2 to 1 will be the minimum value, right? And obviously from this equation, you see, right, E is equal to hc by lambda. If E is minimum, lambda will be maximum, right? Now that is the reason why we tell that, and whatever be the transition, whatever be the series, right, for getting minimum energy, the transition has to happen from the whatever the shell to the minimum shell number. Say for example, in this case, Lyman series, n is equal to n1 is equal to 1. So from 2 to 1 is where I'll be getting the minimum energy. Right. For if I talk about Balmer series, right, the minimum energy, there is no transition from 2 to 1. Obviously, this is gone. N1 is gone. All I have is 2. So 3 to 2 will be the energy minimum value. And all the other transitions, say this to this, 5 to 3, 5 to 2, or 4 to 2, all of them will have higher energy. Right. So minimum energy will be getting only from the consecutive transitions, say 3 to 2 or 2 to 1, like that. Right. So that's why we say for minimum energy or for maximum lambda, N2 value should be is equal to N1 plus 1. Yes, understood, everybody? Why is it like
Understood,
this?
sir.
Right, good, good, right. So same way, I can do now for lambda minimum or energy maximum. Correct? Right, lambda minimum or energy maximum. Now, when that will happen? Now, the maximum possible energy for Lyman series, if I take, say I have so many energy values. Say if the electron comes from some highest orbit, and I can consider the highest orbit as infinite orbit, right? So from infinite orbit, if it comes to n is equal to 1, that only will have energy maximum. And if I have energy maximum, I'll have lambda minimum. Right? So remember, for lambda minimum of energy maximum, N2 value is infinity. Very simple. Right? Wherever it is, like it has to start with infinity, and depending on which series you're talking about, for Lyman series, it has to come to the first orbit. For Balmer series, it has to come to the second orbit. Like that, whatever be it, but the N2 has to be infinity. Where it comes from should be infinite orbit. This is for minimum lambda and maximum wavelength. Sorry, minimum wavelength and maximum energy. And for lambda max or energy minimum, N2 should be equal to N1 plus 1. This two.
Sir, I have a doubt, sir.
Yeah, please tell me.
Sir, suppose an electron is present in the third shell and it comes to second shell first and then it goes to first shell. What is that series called?
There is no series like that. It is just the transition. So basically, if I tell you that the electron is in third orbit, okay, and it goes to second orbit and then it comes to first orbit, I still call it as Lyman series. The end result is what you have to see, right? End result is what? It is coming to n is equal to 1. So whenever it ends up with n is equal to 1, it is Lyman series. It doesn't matter what, like, say how many transitions are happening and I end up with n is equal to 1. As long as I end up with n is equal to 1, it is Lyman series. Yes, understood?
Yes, sir.
Okay, good. Right, fine. So I hope you all understand what is this, and we'll do some, definitely we'll do, we're going to do some couple of problems on all of this. Okay, right, fine. Get ready for problems. Okay, take down the question. Wave number for a transition, wave number for a given transition. Just take wave number for a given transition, wave number for a given transition is x per centimeter. The wave number for a given transition is x per centimeter for He3 plus, sorry, for He plus. Okay, for He plus. Right. Now the question is, for the same transition, for the same transition, for the same transition, what is the value for the same transition, what is the value of wave number for the same transition, what is the value of wave number for beryllium 3 plus? Okay, so they are telling there is some transition, say 2 to 3 or 4 to 3 or whatever it is. Okay, some transition is happening. For that, the wave number, they got it as x per centimeter. Right? Now, for the same transition, say for example, it is 4 to 3. Here also it is 4 to 3. Right? But I know I need to know what is the u bar value for this. In terms of x, obviously, I have to say. Okay, do it. Tell me the answer. So here N1 and N2, whatever be the N1 and N2 here, the same N1 and N2 are here also. Okay, this is the same transition. Right? Keep that in mind.
So,
Yeah. Your voice is breaking down. I'm not able to. Can you put in the chat box if you're okay? I can see. I can look into it. There is something in the chat box. 4x. Okay, fine. We'll check it out. 4x options are there. Right. It's a very simple problem. Right. Let me do it for you. Right. Say for He plus, we'll try to calculate first. Right. Now, what is the, so basically the formula goes like this. Mu bar is equal to RH Z squared. Mu bar is nothing but 1 by lambda. Right. Anyways, so now RH Z squared into 1 by N1 squared minus 1 by N2 squared. No problem. Okay. Now let me substitute. So this value is what is given as X. Okay, this value mu bar for He plus some transition N1 and N2, the value is given as X. So how will I write? RH is some constant. Now Z alone will change. What is Z? For helium, it is 2. So Z squared will become 4, right? So it will be again same N1 squared minus 1 by N2 squared. Okay. So now we found out, right? Fine. So now look at this for beryllium 3 plus, right? For beryllium 3 plus, mu bar is equal to RH Z squared. Now for beryllium, the Z value is 4. So now it will become 16, right? Now 16 into 1 by N1 squared. I'm not changing N1 and N2 because it is the same transition, right? 1 by N1 squared into 1 by N2 squared. Okay, now see, I can see, look at this. 4 into RH into 1 by N1 squared into 1 by N1 squared is what is X, right? Now, can I write like this for beryllium? Mu bar is equal to 4 into RH into 4 into 1 by N1 squared by 1 by N2 squared. Okay, now if this you do, now look at this part alone. If you look at this part alone, you look at this RH into 4, RH into 4, 1 by N1 squared, 1 by N2 squared. So this entire value is X. Is it not? That is what is X, right? So now what is the lambda mu bar for beryllium 3 plus? 4 is already there. And this entire thing is X. Yes, the answer is 4X. Very simple problem. Very, very simple problem. Okay. Right, I hope everybody understood. Nothing. 2 times using the formula and just smartly calculating. That's it. Very simple. Right, I hope everybody understood. Right, next problem. Maybe you just take this down. Maybe I'll give you a minute and then we'll go for the next problem.
So in P fund series, N1 is 5, right?
For what series?
P fund.
Fund. It's not P fund, it's just fund. P is silent. Yeah, N1 is 5. Right? Okay. Okay, if you've taken this down, I can give you the next question. Okay, take the question. In Lyman series, shortest wavelength in Lyman series, shortest wavelength of hydrogen atom, appears at X meter. Okay, in Lyman series, the shortest wavelength of hydrogen atom appears at X meter. Okay, some X. Right, now the question is, find the longest wavelength. Find the longest wavelength in Balmer series. Find the longest wavelength in Balmer series for He plus ion. Right? Find the longest wavelength in Balmer series for He plus ion, not for hydrogen. Right? For He plus, right? For He plus ion. I'll repeat the question, people. In Lyman series, the shortest wavelength of hydrogen atom appears at X meters. Right? So find the longest wavelength in Balmer series for He plus ion. Okay, so you know what values you have to take for Lyman Balmer for shortest to longest, right? Everything is given to you. Just apply the formula very simply, very easily. You can do this. Very simple. Obviously, the answer will again come in terms of X. Okay.
So is it x upon 5?
X upon 5? No. I think you're missing that. You're finding it for He plus, I guess. No, you're not finding it for hydrogen. You're finding it for He plus. So the Z value will be different, right? Let me see if anybody can give me the correct answer. Yes, do not sit idle. Again and again, I'm telling, there is no point in you sitting in idle, right? This time is given to you. It's almost like I can in this time I can finish some 2-3 concepts, right? I'm giving you time because you need to practice, right? Go for it. Do not sit idle. Let's give you 2 more minutes, people. Let me see if anybody can get the answer correctly.
So is it 5x?
No. X by 5 is partially right, but it's just not X by 5. Something else is there along with it. And yeah, one more thing I want to tell you, the problems we do in class, right? Whenever I teach you the problems we do, these are little higher level problems. Okay. So if you do not get the answer, do not get demotivated. I'm telling you, if you are able to solve and at least understand how we are doing the problems here, your school problems, school exam problems are very easy. Trust me on that, very easy. Okay, so don't get panicked looking at the questions. Like the quality of questions we solve is a good quality questions we solve in class, right? Obviously, tougher things, if I can help you and you can solve it. Obviously, easy questions you can solve by yourself, right? So that's the reason why we do only good quality problems. I can just give you normal formula substitution and ask you to do it. There's no point in doing that, right? So that's why we do it like this. So don't worry if you're not able to get the answer. All thing that matters is that you're trying, right? That's all that matters. Okay, I think I'll do. Anybody needs more time? Anybody is close to getting the answer? Anybody needs more time?
Sir, 5 upon 9x.
5 upon 9x is 9x by 5 is what you're telling? Is it 9x by
No.
5? Like this?
1 second. Sir, I think I'm getting 5x by 9.
5x by 9. Okay, fine. We'll check. The options are there. That both 5x by 9 and 9x by 5, both options are there. We'll see how we're going to do the problem. Okay, cool. So they are telling that I have Lyman series for hydrogen and I'm going to get lambda minimum. That's what it is, right? Yeah, the shortest wavelength. That is lambda minimum in Lyman series for hydrogen atom. So many informations here. Okay, now we know for lambda minimum, right? For lambda minimum, I should have the n, obviously for Lyman series, n1 is fixed, n1 is 1. This comes from the Lyman series. Now for lambda minimum, how should be the n2 value? N2 value I showed that it should be infinity. For lambda minimum, you can see here, where is it? Yeah, for lambda minimum, I told you that n2 should be infinity. N1 depends on what series you're talking about. In this case, n1, in this case, you're talking about Lyman series. So n1 is equal to 1 and your n2 will be infinity because I'm having lambda minimum. Right? Now this you must understand. Okay, now you can go for the formula. Now since you're talking about, how are you doing it correctly? Once again. Okay, yeah, you're doing correctly only. Fine, right. So for 1 by lambda minimum, and we are doing it for hydrogen, it is equal to RH Z squared. Z squared is 1, right? Because hydrogen atomic mass is 1 into 1 by N1 squared. N1 I know is Lyman series, 1 by 1 minus 1 by infinity squared, which is going to become 0. No issues, right? Now, see, now I have 1 by lambda minimum is nothing but RH. And see, they have given the lambda minimum as X value. The value is given to you. That is lambda minimum is given as X, right? So can I write 1 by lambda minimum? In this place, if I put X, so basically RH is nothing but 1 by X. Or I can write X is equal to 1 by RH. Till now, is it okay, people? Or I can, whatever it is, RH, I can write as 1 by X or X and write as RH. Okay, so this is easy. This is coming from the calculation. What I did, I know it's Lyman series. For hydrogen atom, Lyman series means N1 is equal to 1. And minimum value lambda means I should have N2 as infinity. So now I just substitute in the equation. 1 by lambda is equal to RH, Z squared, Z is 1. So 1 squared will be 1. N1 is 1. And in N2 is infinity, so this becomes 0. So all I get is 1 by lambda is RH, right? And they have given the lambda minimum value as X. Okay, so basically I have RH is equal to 1 by X. This equation you can remember. This will be a good equation to use. Okay, right. Now we'll go for the next case. What they are telling, I must go for lambda max for Balmer series for He plus ion. That is what they're telling, right? Lambda max I need to find in Balmer series for He plus ion. Okay, now first things first, for Balmer, N1 is 2, right? And since it is lambda max, N2 will be N1 plus 1. And in this case, N1 is 2, so N2 is 3, right? So for lambda max, I told you N1, N2 should be N1 plus 1. Now, since it is Balmer series here, N1 is equal to 2. So obviously N2 should be 3. That is for lambda max, right? For lambda max, no issues. Okay, now that's it. Now we have to substitute in the equation. So 1 by lambda max for He plus will be equal to RH Z squared. Now Z squared, helium Z is 2. So 2 squared will become 4, right? Into 1 by N1 squared. N1 squared, 2 squared will become 4 minus 1 by N2 squared. 3 squared will become 9. No issues. Now, RH value I can substitute in terms of X. You can see here, RH from the previous calculation, I got RH value as 1 by X, right? So I can write it like this, 1 by lambda max for He plus RH is 1 by X into 4 into 36, 9 minus 4. That's what I'll get. So I'll be getting 1 by lambda max as 4 by X into 5 divided by 36. Okay, so now this 4 and 36 will go 9 times. Okay, now what I get is basically 1 by lambda max as 5 divided by 9x, right? 1 by lambda max as 1 by lambda max, what I'm getting? 5 divided by 9x. So what is lambda max is what they're asking. That will be reciprocal. So that would be 9x by 5. Very simple. Okay, right? Lambda max, we got the value as 9x by 5. So the answer to this question is 9x by 5. Okay, again, I repeat what I did, people. So first things first. So they gave the lambda minimum value for Lyman series for hydrogen atom as X. Okay, now for Lyman series, I know N1 is equal to 1. And since it is lambda minimum, N2 will be infinity, right? So I substitute in the equation 1 by lambda minimum for hydrogen is equal to RH into Z squared. Z is equal to 1 for hydrogen. Now I substitute the N1 and N2 values. 1 by N1 squared, 1 by 1 minus 1 by infinity will become 0, right? So from this, I got the lambda m value is given to you. Lambda minimum value is given to you as X. So RH is nothing but 1 by X, right? Now we'll use this equation the second equation. Anyways, now next thing what they tell is lambda max. You have to find the lambda max for Balmer series for He plus. Okay, so for Balmer series, I know N1 is equal to 2, right? And lambda max, if they ask you, that should be N2 should be equal to N1 plus 1. In this case, N1 is equal to 2. So N2 value is 3. Okay, so now we'll do the same equation. 1 by lambda is equal to RH Z squared into 1 by N1 squared and minus 1 by N2 squared. Now we are using for lambda max. So RH, I will substitute as 1 by X from the previous equation, right? And N1 and N2, I know 2 squared will become 4, 3 squared will become 9. I do the calculation. I get lambda 1 by lambda max as 5 by 9x. So obviously lambda max as 9x by 5. Okay, now I want S from everybody, right? Either in the chat box or unmute and see if you understood. Just for my satisfaction. Everybody understood, people? Can I get a yes from everybody?
Yes, sir.
Okay, S1. I got another S2. I have how many people? Okay, 3, 4,
Yes, sir.
5, 6. Oh, and there are 13 people. There are 7 more. Everybody understood? Okay, 7. Six more are there. Yes, please tell me. You can, at least for this, you can participate. You just have to type a yes or no. Everybody is okay. I can still pick names, people. I know who all said yes. Still, I can pick names. Is everybody okay? It is for your side. This thing only I'm asking. If you didn't understand, I'll explain again. That's the point, right? Is everybody okay? Fine. Okay. Maybe you don't want to answer. Maybe because you're either like whatever. Anyways, fine. So I hope everybody understood, right? So the value would be 9x by 5. That's the thing, right? So yeah, that is about Lyman series, Balmer series, emission spectrum of hydrogen. With this, the Bohr's atomic model ends. Okay, that's about the Bohr's atomic model. Okay, right. Now what we'll see now is about the drawbacks. And yeah, before that, I wanted to ask, guys, did you get to know that you will be writing the exams in 2 terms, first term and second term? Like yes, from sir. The government, they gave the order, right? So did they give you the list of chapters which you'll be seeing in first term?
I got the PDF.
You got the PDF. Okay, can someone look at the PDF and tell me what are all the chapters which are there for the first term? So that I can also know if someone has the PDF with you now.
Sir, just a minute, I'm just checking.
Sure. Please take it time.
So for first term, we are having some basic concepts of chemistry,
Okay,
Structure
basic
of-
concepts, structure of atom, Hmm.
classification of elements and periodicity,
periodic table, okay,
then
Then?
chemical bonding and molecular structure,
okay, chemical bonding, then,
redox reactions,
okay,
hydrogen,
hydrogen, seriously, okay, fine, then,
and then organic chemistry, some basic principles.
oh, some basic principle, GOC, okay, fine. So
That's
only this, that's
Yeah,
it?
that's it for
Okay.
first term.
Fine. So with this we completed, this we'll complete in another 3 classes. Periodic table is very easy. Chemical bonding is very interesting. Redox is a very small chapter. Oh God, hydrogen people, right? There is no point in teaching that particular chapter. It is so boring, right? So what we'll do for hydrogen is we will have a quiz. Okay, quiz in the sense you will study the entire chapter and come. Like before that, I will segregate you into say 2-3 groups. We have almost like 14 people, 12 people, say 3 or 4 people in a group. So like that, we can have a quiz for hydrogen alone because it is so boring to teach. It is so boring to listen. The chapter is like that, full theory. Okay. Other chapters, yes, I'll definitely teach you. Redox, GOC, chemical bonding. Yeah.
So they've also given the mark allotments for these chapters.
Okay. How much mark allotments?
So for basic concepts of chemistry, it's 11, and
11 marks.
structure of
Okay.
atom, it's 11.
Okay.
Classification of elements, 4.
4. Okay.
Chemical bonding, it's 6.
6. Okay.
Redox reaction and hydrogen, it's 5.
Together it is 5. Okay. Fine.
And
for GOC?
organic chemistry, it's 9.
9 marks.
And I guess
so
also
max,
for basic concept of chemistry and structure, both are together 11, I guess.
oh, together 11 marks. Okay.
Yeah,
Fine.
it counts up to 35 marks.
35 marks. Okay, cool. So basically the majority is coming from GOC that has the maximum mark, right? All the others are a little lesser mark. Okay, but yeah, this is very important, very important, because like I told you that in 11th you study only 2 chapters in organic. One is GOC, another one is hydrocarbons. But when you go for 12th, you have almost 6 to 7 chapters in organic only. And hydrocarbons and these 2 chapters, if you're going to miss in your 11th, your entire 12th is going to be a nightmare. Okay, a lot of now current students in 12th, right, they are actually suffering because they didn't do the first like 11th part very properly, GOC. Anyways, so this is a good information. I'll keep it. Okay. So now we are going on the correct path, right? Basic concept we completed, our atomic structure we are doing, and then we'll start with periodic table, and then we'll go for chemical bonding. Okay. Redox reaction is very simple. That is a very small chapter. GOC, yes, we have to concentrate. And any date, when will you write the first semester? I mean, first term exams? Any month? Any dates are there?
That is not given, sir.
That was not given. Okay,
Sir,
so
but
we can
mostly in
assume
October or November. Sir.
November, right? Even I am thinking, right? October or November is what we'll have. So we have actually a lot to catch up to. Now it's August. August entire month will be there. September, October, 3 months we have. So 3 months, how many classes we'll get? 1 month, we get 6 hours. Sorry. 1 week we get 6 hours. Sorry, 3 hours. So for a month we'll get 12 hours. So for 3 months we almost have 36 hours. Right, 36 hours. Completing this is a task, right? So definitely people, we need to have some extra classes. Okay, I'll plan for it. Like maybe like weekly I'll have at least 1 hour instead of having 3 hours. If I can have 4 hours, it might make some sense. Okay, well anyway, I'll anyways plan properly and let you know whatever the plan is. This is actually a good thing since I know all this. Okay, good, fine. So now we'll move on. Okay, we'll move on to the drawbacks of Bohr's atomic theory. Okay, now one drawback we already know that it works only for single electron species. right? For if you have more than one electron, all the calculations, everything is wrong, right? Okay. Second one, there is something called as Stark effect and Zeeman effect. Okay, there is something called as Stark effect and Zeeman effect. So that is basically a phenomenon, scientific phenomenon, physical phenomenon, which was not able to, the Bohr was not able to explain the Stark and Zeeman effect. Okay, it is not explained, right? So first we'll try to understand what is the Stark and Zeeman effect. So take down the statements, people. For first for Stark effect. Right? Take down the definition for Stark effect. Right? It is the phenomenon of splitting of spectral lines, It is the phenomenon of splitting of spectral lines in the presence of electric field. In the presence of an external electric field. In the presence of an external electric field. Okay.
Sir, what?
It is the once again, I'll repeat the statement. One second. It is the phenomenon of splitting of spectral lines in the presence of electric field. Okay, what is the question?
Sir, like, what is the name of the phenomenon?
What is the name of the
phenomena?
Stark effect. We're talking about Stark effect.
Okay.
Right? Okay. So what they're trying to say, see, like if at all you want to completely understand this, again, like we don't have that much physics knowledge with us right now. Like, right? I'm talking about you, right? So all you have to understand here is that we know what are spectral lines. In the spectrum, some lines, whatever, due to the transition, some kind of lines you will get. Say, now what happens is, if I apply electric field, what Stark observed is that, say, if I talk about this particular line, right? Now, this particular line got divided into multiple smaller lines. This particular line became like this, okay, when they applied electric field, okay? Now, this is all you have to understand, and Bohr was not able to explain, right? Because for one emission, say from 3 to 2, if the electron goes, there'll be one line in the spectrum, right? But 3 to 2, in the presence of electric field, you are going to get multiple lines. Now, why this happens, your Bohr was not able to explain. Okay, and we will not try to explain this because it is beyond the scope of your 11th class. We will not go into details. Okay, too much it is confusing. All you have to understand is the spectral line is splitting in the presence of electric field, and that was not able to be explained by Bohr. Okay, now Zeeman effect is very, very, very similar to Stark effect. Now the same thing. It is the phenomenon of this spectral line splitting in the presence of magnetic field. That's the only thing. Okay, so you give electric field, that splits, it's called Stark effect. If you give magnetic field, if it splits, it's called Zeeman effect. Okay, we can take the same statement. It is the phenomenon of splitting of spectral lines in the presence of magnetic field. Just in place of electric field, put magnetic field for Zeeman effect. Okay. Okay. So these two phenomena were not able to be explained by both Stark effect and Zeeman effect. The first thing was obviously all the formulas, all the theory, whatever he told will work only for single electron species. Okay. Next one is dual nature of electron. Okay. Now please understand, Bohr considered electrons to be only particles. Okay, he considered electrons to be only particles. Okay, but when there was this guy called as de Broglie, okay, it is Brogle, right? De Broglie was, say, if I have to put the correct word for him, he is a scientific philosopher. Oh, sorry. Okay, he's basically he is basically expert in philosophy. You know what is philosophy? Giving advice and stuff, like talking about how to live your life and stuff, right? So he was actually a philosopher, right? But he became a scientific philosopher just because of this something called as de Broglie hypothesis. Okay, so what he said is that he said everything in the world is symmetric, right? What do you mean by symmetric? Everything in the world has good and a bad side, or say men, women, good, bad, heads, tails, night, day. Everything is symmetric, right? One side, second side. So sorry, right? So he said entire world is symmetrical. Right? Symmetrical means, as I told you, good, bad, men, women, night, day, whatever it is, right? Summer, winter, whatever it is. So we have entire world to be symmetrical, and so will be light or electrons. Okay, so what he said is that this light, that is normal light which we see, or electrons for that matter, are going to have dual nature. They are also symmetric. Okay, he said that they are going to have dual nature. What is dual nature? One is obviously the particle nature, right? As particles, light or electron can be regarded as a particle, or they can be regarded as waves. Okay, so light or electron has both particle nature as well as wave nature. And how he said it is very simple. He said that the entire world is symmetrical, and so the same can be applicable for a light or electron, because they are also in the world, in the world we live, right? So they are also symmetrical in the sense that they are also going to have dual nature. That means both electron and light will have particle nature. They can behave as particle during sometimes, or they can behave as waves sometimes. Okay, now what happened with Bohr? Bohr considered electrons to be only particles, right? Bohr considered electron only to be particle. So obviously, according to this hypothesis, de Broglie's hypothesis, he didn't take into account in the wave nature of electron, right? He didn't take into account of wave nature of electron. That is also a drawback. Okay, now we can strongly, we can actually see in depth about this de Broglie's hypothesis. So he said that both light, particle nature and wave nature exist for light and electron, right? So we can actually connect two of the biggest equations in scientific history. Okay, what are the two equations? One was your Einstein's equation, E is equal to mc squared. Right. Another was the Planck's equation, that is E is equal to hc by lambda, or E is equal to h nu. I know lambda, mu is equal to c by lambda. Okay. So if both of them, say you are talking about one particular light or one particular electron, now both of them have both the natures, right? So electron has both the nature, light has both nature, right? So these two energies can be equated, right? These two energies can be equated because both of them are coming from a single electron. Both of them, I mean, this electron has both the nature, both particle. This is for the particle nature, right? This, what is the E is equal to mc squared is for particle nature. And this I know is obviously for waves, because lambda will be existing for only for waves, right? And mass will be existing only for particles, right? So if I combine these two and I equate it, right? mc squared is equal to hc by lambda if I equate it. So c squared and 1c gets cancelled. So basically I'll be getting lambda is equal to h by mc. We write c, but everything will not be, if it is light, okay, it is moving in the speed of light. For generalization, we can write v, some velocity, right? If it is light, we can write c, obviously, we'll say a velocity of light. If not, we generally write v. Okay, now this lambda is equal to h by mv. This lambda is what is called as de Broglie's wavelength. Okay, this lambda is what is called as de Broglie's wavelength. And what he did, he just connected two of the most important equations for energy in the scientific history, and he got this particular equation. Lambda is equal to h by mv, or I can also write it as lambda is equal to h by p, where p is the momentum. Is it not? I know momentum formula. P is equal to what? mv, right? Mass into velocity is what is momentum. You can see mass into velocity is there. So I can write lambda is equal to h by p. Okay. Now he did nothing. Like all the efforts were done by Einstein and your Planck, but they didn't get the Nobel Prize. Okay, but just by connecting these two equations, de Broglie got the Nobel Prize. Right? This is how science works. Anyways, right? So he for this de Broglie's hypothesis, de Broglie's wavelength, he got the Nobel Prize. Okay, nothing. De Broglie showed nothing but lambda is equal to h by mv. Right? Mass of the particle, velocity of this thing, h is Planck's constant, everything we know. Okay, so this is also a problem with the dual nature of electron is also a drawback of Bohr, because Bohr considered only electrons to be particles, but de Broglie proved or de Broglie hypothesized that electron can have wave nature also. Okay, and this was the basis, this was the starting point for the theory which we follow currently. Right, I told you that there's something called as quantum mechanical model. Right, so there we actually consider both the things, both particle nature as well as wave nature of electron, and then incorporate it, and then we got the theory. Right, that we'll see in a little while how what do we do.
Sir?
Yeah, tell me.
Sir, by after equating both the equations, we get lambda is h upon mc.
Correct. But we wrote mv.
Sir, then
So
how
ask
did
why
he
you-
convert c into v?
Oh, nothing. So the thing is, C is particularly for light. If you are going to speak about light, yes, we can use C. Actually, like it's not like anybody can do it. Not only him, anybody can do it, right? This is a general equation, right? This is a general equation. If I write h by mc, we can speak only about light and nothing else, right? So he wanted to give a generalized statement. That's why he converted the C to V.
Sir?
That's it. Yeah.
Sir, then in case of energy of an electron, it should be h velocity of electron by lambda, right?
Sorry, come again.
Sir, E is given as E equals hc upon lambda. So in case of
Yeah,
energy
hc
of
by lambda.
an electron, then the C should be the velocity of an electron, right?
Exactly. This C should be velocity of electron, right? But what you have to understand is all electromagnetic radiation, all EM waves generally will move in the same this thing, 3 into 10 to the power 8. Okay, all electromagnetic radiation, say gamma rays, X-rays, light, UV rays, everything, right? They generally almost, not like all the time, but say most of the time, you will see that they will move with this velocity only, 3 into 10 to the power 8, right? An electron, if you see what is gamma rays are nothing but electrons. Okay, so they also will move approximately in the same way, same speed only, 300 to the power 8 meter per second. But again, yeah, obviously it depends on the medium. Vacuum, definitely. If at all I have vacuum, all these things will move at the same speed, 300 to the power 8. Okay?
Yes, sir.
Right? Fine. So yeah, this is de Broglie's wavelength, lambda is equal to h by m. We will do some problems, but I don't think we can do it today. We have 20 more minutes only, but we'll just complete all the drawbacks of Bohr's atomic model. So first one was single electron species. Second one was Riemann and Stark effect. Third one was dual nature of electron. And the fourth and most important one is Heisenberg's uncertainty principle. Okay, Heisenberg's uncertainty principle. Okay, so he did a very famous experiment. Okay, Heisenberg is a scientist. He did a famous experiment called cat in a box experiment. You must have heard it, right? It's called what cat? It's called Heisenberg's cat. Oh, whose cat it is? Oh God. No, it's called Heisenberg's cat. Schrodinger's cat. Okay, so he was the first one to develop the experiment. Basically, Heisenberg took the idea. Schrodinger took the idea, and like basically the next theory which we're going to see, the quantum mechanical model, right, is given by Schrodinger. Okay, so this particular thing is the basis for quantum mechanical model. Okay, anyway, so we'll see what is this cat in a box experiment. Okay, I think most of you will know, but still we'll see, right? So I have a box. Okay, so inside this, I put a cat. Please bear with my drawing, people. This is a cat. Okay, and there is a small hole. Through this, I give some poisonous gas. Okay, there is a box. Okay, this box is sealed, and inside this box, I put a cat, and through a small hole, I give a poisonous gas. Okay, right. Now, if I ask you, right, say after half an hour, right, after 30 minutes, this box is entirely sealed. You will not be able to see what is inside, right? So after half an hour, after 30 minutes, if I ask you the question, what do you think the cat is dead or alive? If I ask you the question, what your answer would be?
Dead.
Yeah, dead, right? So that's what we think. But people, are you 100% sure that the cat will be dead? Are you 100% sure that the cat is dead?
At this stage of death.
Yeah, we can tell, yeah, maximum probability. Probably, most, we can, the statement, if you ask me, I would have told, most probably, the cat is dead. This I'll say, but I will not tell, for sure the cat is dead. Even if I say it, I am a stupid guy. Like, I should not be saying it like that. Why is it like this? So as long as you open this box and see, you cannot tell whether the cat is dead or alive. Okay, so unless and until you open the box, you cannot tell. So if the box is closed, right, the cat is in a state where it is both dead as well as alive, right? So what I'm trying to say by both dead or alive is that there are some chances that the cat might be dead, or there are some chances that the cat might be alive, right? So all you can talk only is in terms of probability. Okay, all you can tell is in the form of probability. You cannot tell anything for sure as long as you open the box and see. Okay, so till you open the box, right, the cat is in a state of dead, or both dead and alive. It's not or alive, it's both dead and alive. That means what? It has both possibility of being dead and both again possibility of being alive also. Okay, so this, what you understand is this death and life are two opposite quantities, right? They are opposites. Death and life are opposite quantities. Okay, and you are trying to measure, right? You are trying to measure them simultaneously, is it not? You want to know whether the cat is dead or alive without even seeing it. You are trying to measure, in the sense you're trying to trying to investigate whether it is dead or alive, right? And you see, this death and life are two opposite quantities. Okay, so based on this experiment, what Heisenberg said to take down, I'm going to give you the statement. Like, based on this, whatever we did in the cat in the box experiment, right? As long as we see, open it and see, we don't know, right? Okay, so based on that, Heisenberg gave his own principle, and that is what is called as Heisenberg's uncertainty principle. Take down the statement, what he said. No two conjugate quantities, okay, no two conjugate quantities can be measured. No two conjugate quantities can be measured simultaneously. No two physical quantities, no two conjugate quantities can be measured simultaneously with 100% accuracy. With 100% accuracy. Okay, I'll repeat the statement, people. No two conjugate quantities can be measured simultaneously with 100% accuracy. Okay, so what is this? Yeah, please tell me.
Sir, you're telling that this is Heisenberg's uncertainty principle, sir. But why is
Yes.
it called Schrodinger's cat, sir?
Yeah, so the thing is, like he was the one who actually constructed this experiment and all. He wanted to do this, right? But actually, this became famous, right? The cat in the box experiment became famous only after Schrodinger published his paper, right? That right? The scientists publish their own research papers. Okay, so
Yes.
even though your Heisenberg's conducted the experiment first, but it was published to the public only by Heisenberg, sorry, only by Schrodinger. That's why it's called Schrodinger's cat. Okay, that's how the history goes, right? Some people will do like this, right? So all we see is only the scientific things, but there are a lot of politics which goes inside. Not only here, even now, even though I am working with scientists, right? There's a lot of politics. I don't have to go into the details. Anyways, so yeah, so if you look at the statement, right, what it says is that no two conjugate means opposite. Okay, so no two conjugate quantities can be measured simultaneously, means at the same time. Right? At the same time, if you try to measure two opposite quantities, you cannot measure them with 100% accuracy. That means what? There will always be some error in doing that measurement. Okay, so one you understand is death and life are obviously two conjugate quantities. If I go to physics, right? If I go to physics, there are two sets of conjugate quantities. One is position and momentum, right? The second set is energy and time. Okay, now how these are opposite quantities, again, it is beyond the scope of your 11th class, people. Don't worry about it. Okay, for now, all you have to accept the fact is that position and momentum are conjugate quantities. Energy and time are conjugate quantities. So what I'm trying to say is that if you try to measure position and momentum of a species simultaneously, you measure the position, you measure the momentum at the same time, you will not be able to do it with 100% accuracy. Okay, there will always be some error, right? Okay, now keeping this in mind, if you go for now, why does it come under drawbacks for Heisenberg's, sorry, drawback for Bohr's atomic model? What Bohr did, he found out the radius of electron, the radius of the nth orbit, so he knows where the electron's position of electron is known. And he also said something about angular momentum, which is equal to nh by 2 pi. Right? So if at all I apply these two formulas simultaneously, I will be able to find the position. I will be able to find the momentum. But that, according to Heisenberg's uncertainty principle, is not possible. This is absolutely not possible. Even if you do, right? Even if theoretically whatever he can calculate, but that value is no way close to the real value. Whatever the exact value, we don't know the exact value first of all. So for sure, the value which you're going to get for Rn, the position and the momentum, are going to have some error for sure. Okay, that is obviously energy and time. Like energy and time, will not generally use it in this particular this thing, but they are also conjugate quantities. Okay, so you will not be able to find the position momentum simultaneously. Even if you find that is not a correct value, there's always some error. Okay, that was the problem with your Bohr's atomic model, because Heisenberg said this. Right, now he even gave an equation, right? That error, right? He said that some minimum error will always be there. Minimum error will always be there. Okay, so he said if I multiply the error, this is error, or I can call it as uncertainty in position. Okay, this is the error value, delta x is the error value, or I can call it as uncertainty in position. If I multiply it with uncertainty in momentum, okay, if I multiply these two, delta x is the uncertainty in position, delta p is the uncertainty in momentum. He said there will always be some minimum value. Minimum value, obviously, the minimum value, the error will be either this or greater than that. So the minimum value, I can write this equation as h by 4. This is what is my Heisenberg's uncertainty principles equation. Okay, so the minimum value of error is h by 4 pi. Okay, h is a constant, pi is a constant, 4 is a constant. That's the minimum value. Okay, so if you try to measure the position and momentum simultaneously, the errors of them, the errors in position, errors in momentum, if you multiply them, the minimum error, the minimum multiplication error you will be getting is h by 4 pi. Okay, this is a very, very important statement. And I can rewrite this statement in a little different way. I can write del x, right? Now del p, how can I write? I can write del of m into v, which is that, I'm sorry, which is greater than or equal to h by 4 pi, right? Now there obviously mass is a constant value, right? Mass will not change, correct? So I can take it out of the delta. So I can write delta x into m into delta v, because obviously velocity will be a problem. Velocity can be different and the error can be there, but error in mass might not be there, right? So this will be equal to h by 4 pi. You can write it like this also, right? So here we're talking about mass of electron. This value we know already, right? If you're talking about electron, we already know the mass of electron, right? So the position of electron and the velocity of electron, if we try to measure them simultaneously, there'll always be some error. That is indirectly we can tell from this, from P. Okay, same way I can do it for energy and time also. Same thing will come. Del E, that is uncertainty in energy, into uncertainty in time, will always be greater than or equal to h by 4 pi. Same equation, but this will not be using much. This will be using in your problems for 11th class for sure. Okay, right? So that is about Heisenberg's uncertainty principle. So you can understand what and all are the problems coming from the first. First was the single electron species. Second was Zeeman and Stark effect was not explained by Bohr. Third one was dual nature of light, de Broglie's hypothesis. We got de Broglie's wavelength is equal to h by mv, right? And at last, the fourth problem and finally important problem was Heisenberg's uncertainty principle. So according to Bohr, according to his theory, he was able to measure the position and momentum, that is Rn and MVR, simultaneously, but that is not possible according to your Heisenberg's uncertainty principle. There will always be some error, and that error, minimum error, is h by 4 pi. If you multiply the uncertainty in position and uncertainty in momentum. Okay. Now next class, what we'll do is that de Broglie just gave the hypothesis, right? De Broglie just gave the hypothesis that our world is symmetrical, so is light, and he gave some equation. So what we'll do to next class is that we will see certain phenomena, right? Certain phenomena proving to you that light or electron is a particle, and also we'll see some evidence or proofs that electron can be a wave also, or light can be a wave also. Okay, actually we will not be concentrating on the fact that the light can be wave, that you will be seeing in your 12th class physics, right? But I'll mention it, like I'll give you an entire idea, but we'll concentrate on the fact that electron is a particle. We'll take one particular thing that is called photoelectric effect. We'll speak about this in detail. I'm sorry, photoelectric effect, right? So this will concentrate on the next class. Okay, and also we'll do some problems on Heisenberg's uncertainty principle. We'll do some problems on de Broglie's hypothesis. Okay, then we'll move on to the photoelectric effect, right? Then we'll move on to the last part of the chapter, that is your quantum mechanical model. Okay, so I might require 2 or 3 classes. I think 2 classes should be sufficient. Okay, so in another 2 classes I'll be completing this chapter for you. Okay, is there any question you want to ask me, people? Anything you want to ask? Okay, so if that's the case, I think we can wind up, right? I'll stop sharing, right? Okay, thank you so much, people. We'll meet again next week. Thank you so much.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, everybody.